Hello everyone. So welcome to this class on signal integrity as part of EE 279 AS, which was taught in UCLA winter quarter 2025. So this particular class is going to be a very long one, and therefore I'm going to try to divide it into multiple sub lectures. And so this is the first part of this lecture. So let us proceed. So yeah, 1 second. Yes. So as we had talked about earlier, what is signal integrity? So signal integrity basically has to do with how we can reliably send signal from a transmitter all the way to a receiver on the other side, which could be between two chips or between two different packages. It doesn't really matter. But basically here, the signal that is sent from the transmitter is usually a digital signal. And as we will see, a digital signal, depending on the rise time of the signal, can have a very broadband frequency spectrum. And so the question is, how can we send the signal at the transmitter side and then reliably recover the signal at the receiver side? Because the signal has a broadband frequency spectrum, the signal undergoes distortion as it travels through the channel. So a lot of these issues will be sort of explored in this lecture, and also methods to mitigate it will also be talked about. So in this diagram, you see basically a typical electrical diagram, equivalent diagram of a package on a PCB. And here you can see this could be, for example, a chip which is wire bonded onto the top metal layer of the PCB. And the PCB itself, this could be a PCB or a laminate, it doesn't really matter, but there are multiple wiring levels. And these multiple wiring levels finally terminate at the BGA, which are which are the final connection to the PCB. So because there are multiple wiring levels and multiple transitions, so for example, here you see there's a wire bond, and the wire bond is typically a long line, and therefore it has some parasitic inductance. And similarly, the various transitions all along the vertical direction as well as the horizontal direction of the package has several parasitics. For example, RLC parameters. There will also be several transmission lines, which we'll talk about, vias, and as well as the BGA ball itself can have its own parasitic inductance, resistance, and capacitance. So what ends up happening is the signal. So imagine this chip was communicating to the PCB or to another adjacent chip. The signal has to travel through several layers of wire bonds and metallization and so on. And so it encounters a large number of parasitics as well as transmission lines along the way, which can lead to signal distortions, as we will see in the next slides. So that's basically what I've talked about here. So you can have chip 1 and chip 2. Chip 1 could have a transmitter on it, and chip 2 has a receiver. And the signal from chip 1 through the transmitter is basically sent through C4 bumps to a laminate and then to the BGA, and then the reverse process happens to go to chip 2. So there are basically multiple signal transitions as shown here. And so if you look at the top view of this entire communication link, what you actually see is you have basically the two chips, and you can have multiple transmitters and receivers on the chip 1 and chip 2. And so not only are there several transitions among within a single link, the two adjacent links can also be very close to each other. So there could be some parasitic capacitance between them. So some amount of the signal from the link 1 can sometimes jump into link 2 because of a phenomenon called crosstalk, which will also be discussed in this presentation. So basically, when you talk about a link, we're going to focus on digital communication link. And this digital link can either be synchronous or it can be asynchronous. The link is said to be synchronous if all the signaling as well as sampling of the data is done in reference to a certain clock signal. And it's asynchronous if there is no clock signal involved, right? So it can occur at any time. So for example, here you can see there is a transmitter which is connected to some power supply, VDD and ground, and the transmitter is connected to the link. And the link, which we will always, throughout this lecture, we'll assume that the link always sends a signal along the Z direction. And then finally, it's received at the receiver side, where there's also its own power supply. So the transmitter, the input at the output of the transmitter, so which is the input of the link, so could be some kind of a digital data as shown here, and it also will also clock signal is also transmitted to is sent to the transmitter and the receiver, and so usually when we talk about a synchronous link, the data is sampled at the rising edge or the falling edge of the clock. And sometimes it can be sampled at both the rising and falling edge. So in this case, I've shown here, it's sampled at both the rising and falling edge, and therefore it's called as a DDR or dual data rate. And you can see at each place the clock transitions, that is the location where we sample the data. So this would be a 0, a 1, 0, 1, and so on. And this is the data that's transmitted. But however, if you see this data can be modeled as some voltage source, which basically has this kind of waveform. And this transmitted signal now passes through some equivalent impedance of the source, which is the transmitter, and then through this entire link, which can be modeled depending on the data rate and depending on the rise time of the signal can behave as a transmission line and hence can be modeled by differential RLGC elements as shown here. And finally, the link that is transmitted goes all the way to the receiver side, where there could basically be some load impedance of the receiver. So this is the entire equivalent circuit of the entire transmission link. And now we need to see, in a sense, what happens to the signal that is transmitted from the transmitter all the way to the receiver. So what happens to Vrx of t for a given Vtx of t? So now, if you look more closely at this signal transmission, so Vtx of t, which is a transmitted signal, you can see here, I've plotted this in the time domain, and you can see that the signal is a bunch of ones and zeros, as we discussed, and it also has a certain rise time and fall time. So the rise time is basically this is basically a representation of the slope. The rise time is defined as the time it takes for the signal to rise from 10% of its value, of its maximum value, to 90% of its maximum value. So imagine that the signal takes longer to go from the 10% to the 90% of its maximum value, then obviously the slope would be less steep if it takes a longer time. And if it takes a shorter time, then you see that the slope, as in this case, would be very steep. So if this signal is now sent through the link, this signal undergoes distortion and the signal ends up looking something like this. So let us try to understand a little bit more how this actually happens. So we know from basic circuit theory that rather than trying to understand how the circuit itself behaves to some kind of a nonlinear signal like this, we like to think of the signal to be in the frequency domain. So we know from Fourier series that any signal, as shown here, can be written as a sum of some kind of Fourier components, which are basically sinusoidal components, having some frequency value. So for example, there could be some fundamental frequency value, which is the lowest frequency, and then some higher order or higher frequency values. If you actually look at this particular digital signal at the transmitter side, and you convert this, if you analyze this in the frequency domain, what you find is that if you plot basically the amplitude of the signal versus the frequency of the signal for this kind of signal, what you will notice is that there would basically be certain peaks in the frequency spectrum at some so-called characteristic frequencies. For example, this would be the fundamental, then the third harmonic, fifth harmonic, seventh harmonic, and so on. And not only would you see that, you would actually see multiple lobes of the frequency spectrum, where the peaks of the lobes occur at these odd harmonic frequencies. And also, you will notice that there are certain antinodes, basically places where the amplitude goes to 0, which corresponds to the reciprocal of the rise time. So depending on this rise time and the reciprocal of the rise time, which is basically just a frequency, that would denote certain places where the amplitude of the frequency spectrum goes to 0. So as you notice here, so the nuances and the details of how this frequency spectrum actually looks like is a part of a digital communication course, so it's beyond the scope here. But you can kind of understand, at least qualitatively, that such a digital signal, depending on its rise time, would end up having a very, very broad frequency spectrum. So if even if, say, the fundamental frequency, which is a clock frequency, is 1 gigahertz, even though the signal, you would expect the signal to have to be a 1 gigahertz signal with a 1 Gbps data rate, the actual link itself experiences a Fourier components that can even go up to 10 times that, or maybe 50 times that. And therefore, in order to make sure that the signal at the receiver side is as less distorted as possible, the link must be able to handle very, very broadband frequencies. And that's really the challenge of signal integrity for these digital signals. So now to understand how the distortion happens, so you have this frequency spectrum of the input digital signal, which is going to be multiplied by the frequency behavior of the link itself, which is going to be, generally, it's going to be some low pass behavior. So it's going to have some gain, uh, some less than unity gain up to a certain frequency, and then you with a very slight sort of fall in the gain. And this is obviously in a dB scale. And then after a certain cutoff frequency, you see that the log of the gain is going to fall rapidly. And this is called the 3 dB cutoff. And similarly, you're going to also have a variation frequency of the phase of this of the link. And so when you multiply this frequency behavior of the link with the frequency spectrum of the input signal, you end up with a new spectrum of the signal, which is the spectrum that is received at the receiver side. And if you basically convert this frequency domain signal to the time domain signal, what you end up having is you end up having some signal delays, some distortions in the signal, and so on. So for example, there could be, so you see this original signal, and these instances where the signals are sampled, which is the which is basically in reference to a clock, would be the same at the transmitter and receiver because the clock is synchronized at both the transmitter and receiver. So you see how originally the signal transitions at this basically at this time instant. But now you see at the same time instant, the signal has been shifted slightly forwards, which means the signal is slightly delayed. And this delay is because of the time it takes for the signal to go from the transmitter to the receiver. Because you know from fundamental electrodynamics that signals cannot go instantaneously, and they have to travel at the speed of light in the transmission line, right? Which is the speed of light in vacuum over the square root of the effective dielectric constant of the transmission line. So therefore, there is this propagation delay, which is related to the time of flight of the signal. And also, because of a phenomenon called as reflections and so on at the receiver, which we'll talk about, and other effects such as crosstalk and electromagnetic interference, you'll find that the signal becomes very noisy and it can have a lot of ringing and noise. And so sometimes, so why is this an issue? So sometimes, for example, imagine let us look at this instant. While the signal was originally should be sampled as a 1, you see that if the signal now kind of oscillates rapidly, as shown here, the signal can sometimes, if the minimum value here is very low, can be sampled as a 0. So a signal that is supposed to be sent as a 1 is now going to be sampled as a 0, and now you're going to have bit errors. So signal integrity is about how to design this link so that you can essentially minimize these kind of distortions in the signal and going from the transmitter to receiver. So you can essentially minimize the bit errors and also other issues with respect to signal recovery. If sometimes you cannot really design the link to make sure that the signal is less distorted, then you have to incorporate other methods to make sure you can recover the data. For example, people use things like error correction and various and other algorithms in the software domain to enable the signal recovery. So I already talked about this, why this is an issue. So this is an issue because, like say you were to sample the signal at some location, then sometimes a signal that's supposed to be a 1 can end up being a 0 and so on. And obviously there are also two effects that happen here. One is the signal gets more noisy as it goes from the transmitter to receiver. The signal is also shifted in time because of the so-called propagation delay, because it takes some time, finite time for the signal to go from the transmitter to the receiver because of the finite speed of light in the transmission line. And also, if you notice, the maximum amplitude of the signal is also reduced at the receiver side compared to the transmitter side because of the fact that the signal gets attenuated as it travels along the link. And what I mean by attenuation is there is some energy loss as the signal propagates along the link, and therefore this energy loss results in a decrease in the amplitude of the transmitted signal. So therefore, in summary, signal integrity refers to how well we can design the link so that as much of the original signal can be recovered. And obviously, before we go on to what are the different issues of signal integrity, and also what are the different ways you can mitigate signal integrity, one common place to start is how can we actually visualize pictorially what the integrity of the signal, pictorially how to quantify or qualitatively see the integrity of the signal. To get an idea for how well the signal is actually being sent through the link. And the way we're going to do this is by a special pictorial representation of the signal called as an eye diagram, which I also like to call as folded onto itself signal diagram. So what I mean by that is, so again, you have the transmitter and then you have the receiver, and the signal that is sent along the link can be represented pictorially by the so-called eye diagram. And what is going to happen is this, and I'll describe how to actually derive this eye diagram or how to actually generate this eye diagram. But the main concept here is that, say you had a bad link. So if you had a bad link and you look at the eye diagram will actually have this. So it's called an eye diagram because you can see it looks like an eye. And what you will find is that if you had a link that was a bad link, which means which means it has a poor signal integrity, then this eye would be more closed. However, if the signal is a good link, where you had designed the link in such a way that the signal integrity, all the signal integrity specs have been achieved, then you will notice that the eye will actually be kind of open like this. And you can define a certain so-called eye mask. And if the eye is more open than the eye mask, then you say that the link has passed signal integrity. So what exactly is the eye mask? So before going into the concept of the eye mask, let us talk about the concept of a unit interval. So the unit interval is basically the smallest interval of the signal where there is both a low to high as well as a high to low transition. So you can assume that this unit interval is just going to be the period of sampling of the clock. So imagine you had a single data rate clock with basically a single data rate clock would be a clock which is sampled only at the rising edge of the clock. And therefore, the time period of the clock would basically be this unit interval. So what we are going to do is we are going to take basically a signal and time domain. Unfortunately, let's see. Yeah. So you're going to have like a signal in time domain, like something like this. And what you're going to do is, remember the unit interval is the minimum interval which has both a low to high as well as a high to low transition. So now, which is also going to be equal to the time period t of the sampling clock. So imagine now you have a sampling clock that's something like this. I apologize for my drawing because I'm drawing using a mouse. So let's say you are only sampling at the rising edge of the clock like this. Then this interval of time is basically called as the unit interval. And now what you can do is you can take the signal and you can divide the signal into a bunch of unit intervals like this. Remember, this is the rising edge of the clock. So you can divide the signal into basically these so-called, and this is called as the unit interval. And this can be done both at the transmitter side as well as the receiver side. And now what you're going to do is imagine these are like, this was a sheet of paper and you had folds at these locations. So now you're going to fold about these folds. So you're going to like fold this on top of itself, on top of itself, on top of itself, and so on. And when you do that, you see, for example, if I fold this signal is now going to come like this. And when I fold this is going to come like this, and so on. And when I fold these signals on top of each other, the signal over an entire duration, over a long duration of time can now be represented pictorically within a finite duration of time, which is the unit interval. And by doing that, you can see how well the signal is behaving over a long duration of time. And typically how this is done in practice is, say you have some link like this, and then you have the transmitter here and the receiver here. remember that the data that is sent here could be any random data. So in order to generate the eye diagram, what you do is you send a pseudo-random bit sequence. So you send basically a series of random ones and zeros. It's called pseudo-random because it's not truly random because it's generated by some kind of algorithm. So it's a pseudo-random sequence. And you send the pseudo-random sequence through this. And then at the receiver side, whatever time domain signal you get, you basically do this folding operation. And then you get the eye diagram representation of the signal. So that's what is shown here. This is a unit interval. So within this unit interval, for example, you can get a 000 or a 100 and so on. And each one of these is a different signal. And then what you do is you basically superimpose all these signals over the unit interval for all possibilities. And then what you do is you end up getting this, which is basically the eye diagram, right? And this is, of course, in a perfect case where like the signals are very sharp, as was shown in this diagram. But in general, the signals are going to have distortion. So they're going to be like oscillatory. They're going to occur at different times like this. And therefore, if you plot the actual eye diagram, it's going to have, mm, yeah. So if you plot the So if you plot the actual eye diagram, as shown here, is basically going to have a lot of like variations along this direction, along this direction. For example, here it could have like signals having different amplitudes. The signals can also occur at different times, and therefore the real eye diagram would look something like this. So now that we have this eye diagram, we can basically define certain characteristics of this eye diagram. Sorry, 1 second. Sorry, just give me 1 second. Okay. Sorry, I'm having a little issue with the annotation. Yeah. So let's continue here. So where was I? Yeah. So now, as I talked about earlier, this is the so-called eye diagram, and therefore you're going to have kind of amplitude variations in the signal as well as timing variations in the signal. So now if you look again at this signal, what's gonna happen is there's gonna be basically some eye amplitude. So the maximum and the minimum of this eye diagram is gonna be called the eye amplitude, also called as the eye height. Actually, yeah, this eye opening is called the eye height. And also because the signal can now occur at different times, you're also going to have this so-called phenomena called as jitter. So jitter is basically when you send the signal at the transmitter side and then receive it at the receiver side, the time of arrival of the original signal transition can sometimes be shifted in time because of certain noise in the link, because of a kind of noise in the time of flight or the delay of the link. And therefore, there's going to be some kind of noise which is represented in time for the eye diagram. And this is going to be called as jitter. And therefore, this is called as the eye width. And so now you can basically define the so-called eye mask, which is this kind of a polygon. And what we can say is that as long as the signal, both in eye height as well as in eye width, is outside this eye mask, then we say that the signal has satisfied signal integrity. Why can we say this? We can say this because what the eye diagram actually does is it tells you where you can actually sample the signal. So if I was to sample the signal exactly midway here, then I can basically tell exactly where I can tell exactly, distinguish the signal exactly when it is high and when it is low. Because I am both in amplitude, I can distinguish a high and a low. And also, I'm far away from where the transitions occur, so that there is some time till when the signal becomes unstable again, which is called as a setup and hold time, which actually will be covered in the CMOS driver design part of these lectures. So the main thing to understand here is that if this eye diagram is more open than this eye mask, then we can easily sample the signal, and the signal will have very less bit errors as well as other signal distortions. And we can easily tell whether the signal is a 1 and 0, and also satisfies the setup and hold conditions for the digital signal. So the eye actually defines the region where you can reliably sample the signal. So here you see the eye opening is quite wide. So the eye width is quite large, and therefore you have a much larger region where the signal can be reliably sampled. In a real link, however, say this was some link you had, some communication link, and you had the transmitter where the data was sent and then is received to the receiver, depending upon where the signal is actually looked at. So say this was the original signal at the original signal at the say this was the original signal at the transmitter. And then as you go from the transmitter towards the receiver, you see how the eye distortion keeps increasing and the eye ends up closing at the receiver. So this is not a good link. So this is kind of like a pictorial way to tell whether a link is designed well or not. So now let us go over what are the various causes of signal degradation. So we talked about these kind of the way we can diagrammatically represent what signal distortion in a link actually is. We talked about the fact that the digital signal that is sent from the transmitter side is quite broadband, and therefore this broadband signal is going to have various frequency dependent distortions as it travels to the link. And therefore, the signal received at the receiver side is going to be quite distorted. So now, what are the various causes of the signal degradation? So one is reflections at transitions. So what I mean by this is whenever there is a change in the impedance in going from basically from one region to another, there's going to be some reflections of the signal. And we'll talk in great detail about this concept of the reflections. There is also the so-called frequency-dependent attenuation, which is depending on frequency, different frequency components of the signal are going to have different values of the loss as they travel along the link, and therefore they're going to be attenuated by different amounts. There's also frequency-dependent time of flight, which was actually discussed in more detail in the waveguides part of these lecture series, which has to do with the fact that different frequency components, so different frequency components of the input signal, and can either end up exciting different modes in the waveguide, or in a single mode, they can have a different field distribution depending on the frequency in the cross section of the waveguide. So they would end up having a different effective index and therefore a different time of flight. And therefore, this frequency dependent time of flight will cause some of the frequency components of the signal to reach at a certain time, and the other higher frequency components could be more delayed. And therefore, this, when you put all the frequency components together to recover back the signal can end up being distorted. There's also a phenomenon of crosstalk. As you'll talk about, there is the next and the fexed, which is basically the near end crosstalk and the far end crosstalk, and we'll talk about these two. There's also the EMI and EMC, which is the electromagnetic interference and the electromagnetic compatibility. There's also the power supply noise and the ground bounce and the ground noise, which will not really be discussed in this lecture, but will be discussed in the lecture on power integrity. And of course, you can have many more phenomena that is also not covered here, which is outside the scope of this particular lecture. So first, let us look about the concept of reflections that occur at transitions. Yeah. So, in order to understand the concept of reflections, let us consider a very simple model of the transmission link. So there's a transmitter here, which is connected to VDD and ground, and there's the actual transmission link, and then the receiver connected to VDD and ground. And this whole thing can be modeled by this equivalent circuit where there is the actual digital signal here. This is the digital signal source. And then there is some source impedance, the transmission line, and then there is a load impedance. So what exactly is a transmission line, which was actually discussed in the waveguides part of this lecture series. So the transmission line is basically the link, and say it's extending from all the way from z equals 0 to z equals L, and therefore it has a length of L. And as we know, because these digital signals that are sent from the transmitter side are quite broadband, the highest frequency component of interest, which is basically which is 1 over the rise time of the signal or 1 over the fall time of the signal, if that frequency has a corresponding wavelength to it, which is much shorter than the length of this link, then the link has no longer can be treated as a lumped element and has to be treated as a transmission line. And therefore, this entire link can be modeled as a transmission line going from all the way from z equals 0 to z equals L. And here I've shown one particular section, differential section of this transmission line, where you can see a bunch of lumped elements, RLGC, going from, say, this is basically one lumped differential element, and this is an adjacent differential lumped differential element. So now what we're going to do is we had talked about what transmission line was in the waveguides part of the lectures, but now we're going to actually mathematically derive what is the so-called telegraph equation that describes the voltage and the current distribution in a transmission line. And we're going to use that analysis to understand what happens when the signal goes from the transmission line to some load impedance of the receiver side. And what you will find is that if the load impedance of the receiver side is not matched, or which means it's not equal to the characteristic, a so-called characteristic impedance of the transmission line, then some amount of the signal will actually be reflected. And that reflection can lead to signal distortions, which is what we are going to try to analyze in the following slides. So now let's look at this model of the transmission line. So we are not looking at the entire length of the line here. We are looking at one small section of the transmission line. So obviously the line itself is going to go 0 to all the way to L, and we are looking at two elements. So one element dz delta z, and an adjacent element delta z next to it, and it's going to have this RLGC. So now let us look at one of these differential elements. So the input voltage is just going to be voltage at the location Z, and the output is going to be the voltage at the location Z plus delta Z. And so now what we can do is for this single section, we can now apply KVL and KCL to solve for what is V of Z plus delta Z, as well as what is the current I of Z plus delta Z in terms of the current I of Z and V of Z. So why we already know we can use KVL and KCL within this differential element of the transmission line, because within this small differential element delta Z, it is assumed that this delta Z is going to be much smaller than the shortest wavelength of interest of the transmitted digital signal. If that assumption holds, then there's not going to be much phase difference in the signal going on either from one side to the other of this differential element, and therefore we can treat this differential element as we can model this differential element as a lumped element model, and therefore KVL and KCL apply. If we take the limit delta z goes to 0, then we go to the continuum case, and the continuum case is applicable for any frequency of the input signal. And we're going to talk about the continuum case to go from this lumped element model to the full transmission line model. So now we can use KVL, KCL in this differential element. So the voltage at Z plus delta Z is just going to be this voltage V of Z minus I of Z times this impedance, which is going to be R plus j omega L times dZ. And you can see this voltage is just going to be the voltage at this node, which is V of Z plus delta Z, is just going to be the voltage at this node minus I times this impedance. That is this. Similarly, what about the KCL? You see that this current I of Z is basically dividing into two, because some amount of the current goes through this conductance in parallel, and some amount is going to the shunt capacitance. And therefore, the current at I of z plus delta z is just going to be this current minus this current plus this current. So it's going to be I of z minus what is this current? It is the voltage across this node here, which is V of z plus delta z over the impedance of this node, which is, but because it's a conductance, the impedance is going to be 1 over G delta z. So I of z minus V of z plus delta z over 1 over G delta z minus the current through the capacitor, the shunt capacitor here, which is V of z plus delta z over 1 over j omega c delta z. Because again, this is a uh, capacitance in shunt, and therefore its impedance is going to be 1 over j omega c. Also, remember, recall from the lecture on waveguides that these RLGC parameters are per unit length parameters. So in order to get the actual resistance, inductance, capacitance, and conductance, they have to be multiplied by the differential length delta z. So now we are simplifying these expressions. So I have simplified these expressions in this form. And now what you can do is, if you look at the KVL equation, you can take V of z plus delta z minus V of z and divide it by delta z. And that is going to be equal to minus R plus j omega L times I of z. Similarly, you can write the KCL expression also in this form. But now you notice something interesting. If you look more closely at this, what does this actually mean? So this is V of z plus delta z, which is the voltage at some location delta z forwards along the z direction, minus the voltage at the location z over the differential displacement, which is delta z. So if I take the limit delta z tends to 0, this is essentially just going to be the derivative of v at the location z. So it's going to be dv of z by dz. Similarly for the current as well. So if I take the limit delta z goes to 0 to go to the continuum case, then I'm going to have dv of z of dz, this is the derivative of v of z at the location z, is just going to be minus r plus j omega I of z. And similarly, di of z by dz is going to be minus g of j omega c v of z. So can you notice here when I take the limit, this v of z plus delta z just became v of z. Is because when you take the limit delta z goes to 0, delta z is going to be much smaller as compared to z. So z plus delta z is just going to be z. So that's why there's a v of z here. Now, whenever you have a differential equation of this form, so you have dv of z by dz being proportional to I of z, and di of z by dz being proportional to v of z. If you notice, this is a very interesting equation because these two equations are coupled, because the current is generating a variation in the voltage along z, and similarly, the voltage is generating a variation in current along z, and therefore these two are coupled. This is very analogous to the coupling you have between the electric field and magnetic field from electrodynamics, right? In electrodynamics, remember, a time-varying electric field generates a magnetic field, and a time-varying magnetic field generates an electric field. And therefore, you get this analogous equation here where the current is generating a voltage and the voltage is generating a current. And whenever you have this kind of situation, it automatically means that you have a wave-like phenomena that is happening here. And you have basically a voltage wave and a current wave that's going to happen. So how are we going to go from this to the next step? We are just going to take the derivative of v dv of z by dz again. So we're going to add another differential d by dz over here. And when you do that, when you do a d by dz over here, there's going to be a d by dz of I of z here. But di of z by dz is just going to be this. So if we simplify this, we get the second derivative of v of z with respect to z is going to be r plus j omega L times g plus j omega c v of z. And similarly, we get a similar expression for the current I of z. And if you notice the form of these equations, they're going to have a d square by dz square v of z minus this thing which can be represented as gamma square v of z, which has the form of a wave equation. And therefore, it describes a wave that is propagating along this transmission line. So we can define r plus j omega L times g plus j omega c. We can define this as being equal to some value gamma square, where gamma is obviously going to be a complex number. And if we write this equation in terms of gamma, we're going to get this with these two simplified wave equations. And if you write down the general solution, and I implore you to go and read up a little bit on the basics of differential equations from any math text, that this differential equation here has a general solution of this form. It's going to have a v of z as some v0 plus, which is just some complex constant times e power minus gamma z, plus another complex constant times e power plus gamma z. And physically, what this means is that the e power minus gamma z corresponds to a wave that is traveling along the plus z direction, and the plus gamma z corresponds to a wave that's traveling along the minus z direction. Remember that gamma is going to be a complex number. And since gamma is a complex number, say gamma can be written down in its real and imaginary parts as gamma is equal to alpha plus j beta. So the alpha term of this complex number is going to cause an attenuation of the signal as it propagates along the length of the link, because it's going to be e power minus alpha z, which means it's exponentially decaying along, the voltage is exponentially decaying as it travels along the link. And the j beta term is going to add a e power minus j beta z, which means the signal is basically essentially gaining a phase and is traveling along the plus z direction. So it corresponds to a wave that is propagating along plus z. So the gamma being complex just means that it takes into account both the propagation of the signal along the z direction as well as the attenuation of the signal as it propagates along the transmission line. So we have basically this v of z expression. Similarly, we have an I of z expression, but here, the constants are I naught plus and I naught minus. The plus and minus here, the superscripts just indicate that it corresponds to a forward traveling or a backward traveling wave. So remember that dv of z by dz is related to I of z, and therefore I of z can be written in terms of minus 1 divided by r plus j omega L d by dz of v of z, and v of z was already written in terms of this. So we can substitute this here and simplify, and therefore we get I of z to be equal to 1 over square root of r plus j omega L by g plus j omega z times v naught plus e power minus gamma z minus v naught minus e power plus gamma z. So now what we have written is we have taken these I naught plus and I naught minus constants, and we have now what we have done is we have replaced them into new constant into an expression which is in terms of v naught plus and v naught minus by using the differential equation that corresponds to how the voltage changes in terms of the current. And so now what we notice is we now notice that I naught plus is related to V naught plus. How it is related? I naught plus is going to be this V naught plus over some impedance, and that impedance is called the characteristic impedance of the transmission line. And similarly, I naught minus is also related to V naught minus by this characteristic impedance. So I naught minus is also V naught minus over Z naught. So now this square root of R plus J omega L by G plus J omega C, if you do some dimensional analysis, has units of ohms, so it has units of impedance, and therefore this is also called as a characteristic impedance, because if you notice here, it is dependent on the fundamental properties of the transmission line, the RLGCs, and therefore it is a characteristic of the transmission line, and so it's called as a characteristic impedance. Also notice if you compare the voltage and current expression, the current expression has a negative sign, but the voltage expression has a positive sign. What the negative sign actually denotes is it actually has to do with charge conservation, because if you work this out mathematically, if this negative sign was a positive sign, then you'll actually have charge buildup in the transmission line. So the negative sign just says that the charge cannot build up at any location in the transmission line because the current is a continuous and steady current. So now, if you look more closely at this characteristic impedance, you notice that remember we had already talked in the waveguide section of this lecture that the inductance per unit length and the capacitance per unit length of the transmission line can be derived from the field quantities, the magnetic field intensity as well as the electric field intensity respectively. So therefore, and the R and G correspond to the loss of the transmission line per unit length. So therefore, the RLGC parameters of transmission line are really a characteristic that depends on the frequency of the signal that's propagating as well as the geometry of the transmission line. So it's truly a characteristic of the transmission line, and therefore this quantity is called as a characteristic impedance. In general, if you notice, the characteristic impedance can be complex, but as we will see in most transmission lines, we will have this characteristic impedance is going to be real because if you notice here, the lines are mostly going to be lossless because, and therefore R, if you set R and G to 0, this number is just going to be a real number. So the characteristic impedance of a transmission line that we are going to deal with here and in practice is mostly going to be a real number. But one important concept to understand about the characteristic impedance is even though the characteristic impedance can be real, that doesn't mean that the transmission line is actually going to dissipate energy, because all the characteristic impedance really is telling you is that it's telling you that the voltage waveform and the current waveform are going to be in phase with each other. But remember, the characteristic impedance is not the same as typical impedance you talk about in a lumped element model. So just because the characteristic impedance is real doesn't mean that the transmission line actually ends up losing energy. It just means that the voltage and current waveform are going to be in phase to each other. So in summary, from this analysis of the transmission line, we obtain the voltage waveform V of Z and the current waveform I of Z as these expressions. And therefore, because we have the voltage and current at any location Z, we can now define a so-called impedance Z at any location Z as going to be just this V of Z over I of Z. So obviously this is going to be some complex number, which is going to be Z naught characteristic impedance times this very complicated expression, which is just the ratio of this over this. So this is a good place to stop for part 1 of the signal integrity series. And in the next part, I will start talking more about how we can go from this concept of the impedance at a given location in the transmission line and go on to talk about signal reflections and also other signal integrity issues. Thank you for your attention.